Okay, so welcome to what would be the last lecture from my side. Of course, somebody may choose to play them in a different order, then it won't be the last lecture. Either way, so last time we talked about optimization, and one thing I promised to you all is that we will do I'll just show you a small visualization of simulated annealing. So I will share my MATLAB screen, which is what I used to do this. Everybody can see my screen, right? Let me just do the, okay, so this is the basic code editor. So this is an optimization problem with three constraints that I have here as a linear and nonlinear constraints. And you will see how they plot. So I will run it. And then the simulator will start, or the simulated annealing algorithm will start with the point 4, 0. So x1 equals 4 and x2 equals 0. And then it'll do 150 iterations of this whole process of trying a new solution, which is perturbing a solution by adding some noise to it, which is this line. And then it'll calculate two objective functions, the objective function for the current point and the objective function for the new point, right? And then it accepts or rejects based on the criteria we discussed earlier. So it'll accept a solution if it is better, always. But even if it's worse, it might still accept the solution. And then we wanted to go just make it a little bit visual. So if you see a blue pentagram, that means that it accepted the solution. Red means it tried it but didn't like it. Okay, so it kept going like that. And then I will start it. I tried to get frames, but somehow it didn't work out. So we'll just see a live demonstration here. So I'll just play it. Hopefully everything works. So it stopped here, and I intentionally stopped it here so that I could show you what the feasible space looks like. So this is the nonlinear constraint, and this is another nonlinear constraint, and this is a linear constraint, right? So my feasible space is this triangular area in the middle, okay? So eventually we want the solution to be found here. And if I recall correctly, the actual solution lies here. The true optimum lies here, which is x1 equals 1 and x2 equals, I think, -4. And it's okay if the solution starts from outside the feasible region, because we penalize it, right? So we have the freedom, let's put it this way, to penalize the solution if it's outside and then have it be reflected in the objective function. So we just, let's say, for example, when we're minimizing the objective function, if the solution is infeasible, we add a large number to the objective function. So obviously it's going to be bad, right? And then the optimizer will reject it. So I will continue this, and then you can see what happens. I'll continue. So it's trying here different solutions. You see there's red dots appearing. So it tries those solutions and they don't work. And now you see suddenly there's a lot of red dots appearing. So if it's infeasible, it becomes red. It rejects all those solutions. And then eventually it stops. So this is the same video playing again. It's almost like, you know, in evolution, we say blind watchmaker, even though this is not evolutionary. It's still, it is just, it just does it by trial and error. Anything outside is bad, so it's red. It keeps getting rejected. Anything that it's so slowly but surely, probabilistically, will find the solution, which is here. We can try some other starting points. So let's say if I start at 4, excuse me, and then I'll just take out this because now we know what the constraint set looks like. So it started somewhere here, 4, 4, right? And then it's going to meander somewhere here, and it's trying. And every once in a while, you see a red dot, and it finds the solution pretty much every single time. Okay, so this meandering is okay. Every time you'll get a different meandering of the solution. And I tried to stress test it. I mean, this is a very, very simple optimization problem, and you expect simulated annealing to be able to solve it. But it can solve more complex problems as well. Okay, so just a demonstration that I promised earlier to you all, and I will reiterate, heuristic algorithms is a very good way to get insights into and trying to understand how optimization process actually works, right? I mean, if somebody's interested, we can just do a 10-10, and then I'll move on to more interesting things. Right, so this is way outside of the feasible region, and let's see if it's able to find it. Oh, okay, found it. So it was 10-10 somewhere here outside, and then once it reaches the So that wasn't enough number of iterations for it to continue and find a solution. Okay, but if I had let it continue, it would have found it, right? So long as it was able to get into the feasible region, you expect it to find the solution. Okay, so that's the demonstration. Anybody that wants any of the codes that I presented in this class, just email me and I'll be happy to share any codes that I presented if you want to get familiar with it. So now we can go to our lecture, which today is reliability engineering. And again, as with any topic we've covered, we get 1 or 2 hours to cover these things that are research areas in their own right. People take multiple classes and do a lot of work in these areas. So obviously we'll only be able to scratch the surface in this case. Okay, and we'll understand basic definitions and the connections it has with probability theory, right? So reliability rests on our understanding of probability theory. Here is where we are. We are at module 6 at this point right now of all these, and then we did some changes. I think that I covered more of optimization. So whatever I covered more of will compensate with Dr. Singh covering topics that were initially assigned to me. But I think the changes are minimal at this point. Okay, so before I start, let me start my stop watch so I keep myself on track. Okay. All right, so this is the outline of my presentation here. So we have uncertainty in engineering systems, a pretty general description of what it means, and then sort of a long-ish discussion of reliability engineering concepts. And then from component reliability, we'll go to system reliability, and then I'll do a brief case study, which is just an exposition of a research project I worked on about 100 years ago. So, all right, so let's get started. So everybody remembers this representation of a system, right? So you have a bunch of inputs on the left-hand side. Let me just get to the pointer. A bunch of inputs on the left-hand side, some environmental variables, and then a single or multiple outputs of a system, right? So system also can output multiple things. That's what we call multi-objective optimization, right? So you have multiple objectives. Okay, so everybody understands that. What happens when the inputs are uncertain? What happens when you think you're going to give a certain input and you aim for it, but it follows a distribution? There's some noise, or more readily realizable is the fact that environmental impact variables are almost always random, right? So there's always some variation associated with that. So what happens to the output? The output will also be uncertain, right? The output will also have some uncertainty. And all the methods that we have done so far, we talked about optimization. Of course, we said we found the optimal solution. If there's uncertainty, the optimal solution may change around, and then whatever we expect may not happen. We solved the optimization problem just now, and it's possible that if you're close to the constraint boundary, you may violate it just because of uncertainty, and that's also a concern in optimization, right? So we call what's called the lean optimum, and then we move the solution away systematically from the constraint boundary to add robustness to our solution, right? So those are the things. And then the other thing also is that from a decision-making perspective, even if it doesn't lead to infeasible systems or system failure, we still don't like uncertainty because we have a utility function when we're using decision-based design approaches, and our utility is defined over these attributes. Because of uncertainty, our utility will go down because most people are risk averse. They don't like uncertainty, right? So modeling uncertainty, no doubt, is important. First, we have to characterize the uncertainty on the left-hand side, know what sort of probability distributions, joint probability distributions are going in, and then propagate that uncertainty through the system to the uncertainty in the output, so we can predict it. If we can predict it, then we can do calculations of what is the probability of failure of the system, what is the probability of this failure of this system over an extended period of time, and so on and so forth. Okay. So, right. So I have this. So just a few examples of what these inputs are like and what the outputs are like. Okay. So uncertainty is pervasive in engineering. Don't doubt that for a second. In fact, a lot of these, even MBSE software, I feel like this is sustainability, sorry, not sustainability. Uncertainty is not fully taken into account. We think that we'll do this and that will happen, right? And this is, but we forget that uncertainty is a big part of engineering process. So uncertainty is a lack of knowledge. We have gone through this process of defining uncertainty and probability. And then a couple of things from a definition standpoint, that if I use the term deterministic outcome, I mean something that has no uncertainty. I drop something, it hits the ground, versus stochastic or probabilistic, when a decision can lead to multitude of outcomes, right? So I do something, it may not result in the outcome that I want. So when I say I aim for a certain X, I can't always reach it. I design a component with a certain dimensions. Manufacturing error causes issues. I make a chip and then it has some errors and so on and so forth. I don't know if you know, when they manufacture chips, especially processors, there's a process called binning, right? So they don't always make, let's say you say 1.6 gigahertz versus 1.8 gigahertz versus 2.4 gigahertz. These big processor companies are not making processors designed to withstand those frequencies, clock frequencies. Essentially, they have the same process, but because of uncertainty, some cannot stop having functioning beyond a certain frequency. So we'll bin them sell them as a lower price alternative. And then some realizations, some chips will actually withstand higher clock frequencies, and then we can sell them at a higher premium, right? But it's the same design.
The new iPhone 16 is binning of last year's iPhone.
Mm-hmm.
The last year's iPhone, whatever waste was there, now they relaunched iPhone 16 at lower price.
Okay. Okay. Right. Yeah. So uncertainty you can sometimes take advantage of uncertainty that way. Okay. So how to incorporate uncertainty in decisions? We need a mathematical model of uncertainty, right? So we don't say generic things that anything can happen, or we don't know what gust loads our system will encounter. No, we actually collect data and then we model these formally before we can use it and make decisions about these systems, right? So engineering systems oftentimes involve large outcomes, large amounts of money. They can risk people's life and safety. So we cannot just be vague. We have to use specific models of uncertainty, which are modeled using probability distributions. Okay. So in engineering, uncertainty means lack of knowledge about the value of a mathematical variable. We've gone through these examples: diameters, gust loads, probability of failure of a rocket motor, probability of failure of a nuclear power plant, probability for being hit by a large meteorite. And this uncertainty must be characterized before one can make a good decision with uncertainty, right? So you have to characterize it, means that you have to put it in the model of probability distributions. Standard ways of doing this is using probability density functions, cumulative distribution functions, moments, and so on. Okay. So I'm assuming everybody has had a statistics class here, knows how to collect data, knows what probability distributions, PDFs, and CDFs of random variables are. Okay. So I'll just give a brief overview, so I won't waste too much time talking about this stuff. So So probability distribution is a description of the probabilities associated with possible values of X, of some random variable X. We're interested in relative likelihood that different values X will take, okay? Hang on, sorry, I have the wrong slide there. So in a Weldon beam example, right, that we did in the last class, we can say how likely is it that we can keep the deflection below 0.03 inches? Let's say at a certain deflection, the system fails. Okay. Well, of course, it's good to know whether what the likelihood of that happening is. So common examples of distributions that we see are uniform. Uniform distribution can be continuous or discrete. Bernoulli distribution, a normal distribution, which is continuous distribution, triangular distribution, beta distribution, Weibull distribution. There's many distributions, right? So it's good to know some standard distributions because we have well understood results and their behaviors are well known, but also know enough of probability concepts to say that sometimes our data doesn't follow any of the standard distributions, right? We should still be able to work with them. We should be able to define their PDFs, such as multimodal distributions or distributions of such type.
So we can use empirical discussion.
Right. Mm-hmm. Okay. So you might already know this, so I will go through these slides fast. So for a discrete random variable, we define probability mass function. For all the discrete values it can take, we assign some probability that it takes a certain value. So you have random variable x. We write random variables with capital letters, realizations with small letters. If it takes realizations x1 through xn, we just mass function basically assigns a probability of it taking each of those values, right? Each probability has to be less than or equal to 1 and greater than or equal to 0. And then the sum of those probabilities is 1, basically saying that at least 1 and at most 1 of those events will happen, right? So, okay. And then we generalize this idea to probability density function, where you have a function of this type, where we can find probability of a random variable x in this case being between two numbers a and b. Okay, so what you do is that you do this integral. These go probability of a being between x being between a and b is this integral of the PDF of the random variable, and which is essentially the area under the curve. And CDF, on the other hand, is probability that the random variable x takes a value less than or equal to the realization. So the argument at the value x, as shown here, is the integral from negative infinity to that point x. Okay, I apologize for the small font. Anyway, so these two describe a distribution. If you have one, you can get the other. So that's the good thing about those. What's the maximum value the CDF can take? Okay, what's the integral of PDF from 0 to 1? 0 to negative infinity to positive infinity? Okay, 1, right? Yeah, so it's 1, right? So the area under the PDF throughout its support is 1. You should know this, and I'm glad that you do. So just a pictorial, what it's going to look like. PDF is here. PDF both have to be positive or non-negative, I should say. The CDF has to be non-decreasing function. PDF can increase and decrease. Okay, and the maximum value the CDF or the cumulative distribution function can take is 1. So I'm sure you're familiar with this. Mean is E of x, where for discrete distributions you just multiply the probabilities with the realization, sum it together, or you can do the integral this way: x times f of x, which is the PDF of the distribution, and then you find means like that. Often we have to find means of functions of random variables, right? So this is again starting to become relevant to the input-output diagram that I showed you, that if you know the closed form expression and it's simple enough, you can find its expectation using this. So here you have a function u of x. You can find its expectation or any moment by just using the concerned formula. Okay, and similarly for variance, right? So variance is expectation of x minus mu squared. For discrete distributions, you'll go like this. For continuous distributions, you'll just do the integral x minus mu squared times the PDF. If you have a function of a random variable, you could similarly find the variance or moments associated with the function of the random variable. So a lot of this is just basic stuff, and you should know this. I'm just covering this as an FYI so that we are primed to talk about reliability engineering, which is the main topic of discussion in this lecture. So I like to provide this visual explanation to my students that when you're trying to do uncertainty modeling, you are essentially dealing with processes that are random. So it could be natural processes like weather, or it could be a human man-made process such as factory outputs. We define the associated random variables, so it could be temperature, humidity, or wind speed, like I show at the top, or it could be number of parts made or the quality of each part. And then we collect realizations. Typically, this is how a lot of distributions are fit, right? So we don't say, you know what, this machine produces normally distributed parts. No, we collect data and we verify, fit a distribution to it to see that that's happening, okay? So we collect realizations and then we draw the mass function. We can draw the mass function, we can draw the bar chart, and then we can see that, you know, we can now use techniques to see if we can fit a normal distribution to it, or we can fit some other distributions. Minitab, MATLAB will do it all day for you, so you don't actually have to do it manually, but sometimes it's good to visually see the data using bar charts and then have a good idea of what your distributions look like. But if you want to use it in engineering design, you have to formally model it. Again, MATLAB or Minitab can do it. If a common distribution type does not fit, advanced methods may be needed to characterize distributions, and you all know that. So we will just stop here. How do we generate realizations of random variables? So now sometimes we have the opposite problem, right? So we have a system where instead of collecting data, we want to generate data so that we can propagate it through the system, right? So let's say in the previous step, you took the data, you did your analysis, you fit the best distribution using any of the many methods we have, and you found that it's, I don't know, normally distributed with this mean, this standard deviation, beta distributed with these alpha and beta parameters and these upper limits and so on and so forth. Once you have the PDF, now you can generate more realizations of it, right? Typically, we don't have enough data for, let's say, a system that has a very low probability of failure. And this is something we do quite a bit in reliability engineering, that we deal with systems that have, I don't know, 1 in a million chance of failure. Of course, we may not have data like that, but you have enough data to fit a distribution, and from that, you can generate more and then propagate it through the system. So some methods are inverse CDF method. So you guys know inverse CDF methods of generating random variables, univariate random variables. So the process is very straightforward. What you do is that you generate realizations of a uniformly distributed random variable. And then for each value, you invert the CDF, because you already know the CDF of the random variable or the target random variable. When you invert the CDF, it gives you the realization. Okay, so you keep doing it many, many times over. There's a simple proof for that. So inverse CDF is used quite often for univariate distributions. Oftentimes, MATLAB or C++ or most codes will generate a random, uniformly distributed random number between 0 and 1. So the RAND function, or the RAND parentheses function in Excel, right? And then you want to generate, let's say, realizations of some normal distribution. So you just invert the CDF of the normal distribution and you get realizations like that, okay? With a given mean and standard deviation, and it'll do that. So that's a pretty interesting practice. Everybody should do that. Norm inverse, yes. Other methods could be rejection sampling. So rejection sampling is, let's say you have a really multimodal PDF, okay? So oftentimes we generate realizations on the support, and then we reject anything that's any point, and then we generate another uniform distribution, if I remember correctly, and then we reject anything that's above the PDF, right? So we generate randomly a point, and then generate another uniform distribution, and then if the uniform distribution is above the PDF, we reject it. And then you have to do some scaling there too, of course. You cannot just do because PDF can exceed 1. Okay, so rejection sampling is again a method. We sometimes use it for discrete distributions as well. Simple way of thinking about this is that this is a brute force method of generating samples of distributions which are not easily invertible. Okay, whose CDF is not easily invertible, and of course you can do computer simulation. Many of these things are already built into your MATLAB, so or any other code that you prefer, and you can just use it directly. Okay, so models help propagate uncertainty. Closing the loop here, that if you have a way of propagating inputs to outputs, you can create realizations on the left-hand side. That'll give you realizations on the right-hand side, and then you can start having an understanding of what distribution the objectives or the attributes that come out of this system, what distribution they follow, and you can go from there, right? What is the probability that, you know, in our case, the pressure generator will exceed this? You can calculate things like that. All right, so okay, so any questions so far? Pretty straightforward stuff, right? Nothing difficult. So we'll start with basic reliability engineering concepts. Okay, so we will return to our Venturi scrubber. Okay, now within this, here's the functional diagram. I like to remind people of the functional diagram here. And then let's say we're interested in the reliability of this subsystem, in particular the Venturi of the subsystem, right? So we're intentionally starting at the component level. So here we were using a Venturi, and we are interested in the reliability of this Venturi because, of course, if it breaks, then the system breaks, right? So we start with a thought experiment. So Einstein was really big on thought experiments, right? You can mentally think about a scenario, and then you can see what's going to happen, and then see if you can think of either holes in a current theory or then some way of extending our current knowledge. So we perform a thought experiment. We say that the scrubber was installed and is running until the Venturi fails. Okay, great. Let's also assume that this failure happens on the 254th day of operation. Okay. Would the Venturi be considered reliable? Would the entire chemical scrubber be considered reliable? Right, so there's two different questions here. One is that, would you say that that component is reliable, and is the entire system reliable, right? Of course, if the component failure leads to system failure, you might say it's not reliable. But at the same time, you have different expectations from components and system. A system can fail in many different ways, okay? So if nothing else failed and only the Venturi failed, you might say the system is generally reliable. So there's many ways to interpret it, and we should not be doing calculations and doing detailed analysis unless we have thought about these things a little carefully. So we continue the experiment. There are a few reasons we cannot answer the question, okay? Nobody should have had an answer so far because the question needed a few more inputs from me. First, we don't know if 254 days is considered long enough period of operation, okay? For some things, it could be considered great, 254 days, that's a long time. We haven't defined what the failure of the Venturi means. It failed. What does that even mean? Okay, what are the different ways it can fail? It cannot create the requisite pressure. Maybe it just barely misses it. Maybe it just explodes and breaks down. Right. Intermittent function. There's a lot of different ways things can fail, right? There's partial failures and things like that as well. And then we don't know how the failure of the Venturi affects the scrubber, which is the entire system. So we will talk about system reliability later. Okay, so that's a separate topic. We first have to talk about component reliability. And then the other thing that was missed in the discussion is that we did not specify what the acceptable operating conditions are. Okay? So we know that the Venturi failed. Okay? Maybe it was subjected to inputs or environmental conditions that was not designed for. Okay? So the whole idea that somebody is saying that system is reliable or unreliable is contingent on the fact that whether it was operated under the specified conditions. What conditions do you think it can fail in? Now that you've lived with this system for almost a week now.
So it was designed in US for Indian environment. So did they consider the humidity in that particular area?
Yeah, so environmental conditions could, so that's the point that is being made, is that environmental conditions could be different from where it was designed. Obviously, they took into account the fact that that in India you use 220 volts, 50 hertz versus, so the motors and all that. Maybe there was particulates, maybe the water was not soft, so it had a lot of dissolved impurities that eventually clogged the nozzle. That's possible. It's possible that the temperature rose too much, right, in the system. That because if you remember, the Venturi was made of PVC, so that may be an issue. Maybe the flow rate was too high. Maybe some other system failed. That's another thing that can happen. Maybe the pH sensor failed, and then the pH kept going higher and higher, and it damaged the Venturi, right? So Venturi itself, whether it's reliable or not, is contingent on a lot of things. What do you call a failure? What do you call a success? What are the acceptable operating conditions? If acceptable operating conditions did not exist, then you cannot make any claim about it. It could be the most reliable thing that you know, but yeah. And then the other thing is that there's also expectation from systems, right? So a lot of companies will give warranty terms knowing that nobody expects this to last longer than this, so why shouldn't we make it more reliable, right? So maybe 254 days is a great Venturi, maybe it set a record. We don't know. So all those things make it difficult to answer questions in black or white. Obviously, we need to think about it a little bit more deeply. Okay, so, and finally, oh yeah, of course. And finally, I was surprised that nobody connected with the whole few minutes I spent talking about uncertainty here, right? It broke. That doesn't mean anything. Maybe it was a off chance, right? If you have field at 50,000 of these systems and one of them failed, that's not a bad statistic. Even if there was some manufacturing defect with it, with the particular Venturi in question, maybe it was an outlier. Okay, so few things. One is, what is the expectation from the system? We don't know what failure means. We don't know how the failure of Venturi affects the system reliability. We didn't specify what the acceptable operating conditions were. And we didn't have enough data to make any determination. Okay?
I want to talk about maintenance. There will be no maintenance, so we didn't do.
Right, but then we can say that comes under acceptable operating conditions, right? So if somebody violated manufacturer specifications or manufacturer recommended maintenance intervals, then that's not acceptable operating conditions, right? So we continue the experiment and think about many components at this time. We already know, and you should know, that it is likely that they will all fail at different times because of randomness in inputs and environmental variables, right? So you can say that a certain car has a transmission issue. Even if it's a known issue, they're not all going to fail at the same number of miles, right? Some may actually last longer, some actually may fail right away, okay? So we continue the experiment, and now we have some data, right? So we have one failed at 254, the first one that you saw, 26 days, 859 days. We got lucky a couple of times with 1200 and 1800, and so on and so forth, right? So now it's all over the place. But we're starting to get a sense of what it means for the what it means, what the distribution of failure time is. Okay, and that's where reliability engineering starts. So, okay, so lessons. Time to failure of components and systems is a random variable. Okay, we already know. When we start talking about random variables, we need to characterize their distributions using probability distribution functions, probability density functions, or CDFs. So you know what's coming there. Its value for a given component cannot be known with certainty. If we knew that this component will fail at this exact time, then there's no uncertainty. Okay, and this is typical of what you would see. I mean, these are notional numbers, but that's what you would see for most components. Manufacturers that would collect data, they would see, okay, well, these are failure times of this part, right? We also learned that, so another lesson we learned is that we need to state acceptable operating conditions before we can comment on component or system reliability. If acceptable operating conditions were not met, then system reliability calculations would not make any sense. For example, if the Venturi should receive a flow between 15 and 25 gallons per minute of water at a temperature between 80 degrees Fahrenheit and 130 degrees Fahrenheit. If this was breached, okay, no fair. You cannot hold us responsible. How do we, before we actually get into that, how do we know these limits, by the way? When you specify, like, your phone probably says what battery will not operate below this temperature or above this temperature.
During the development stage, they must have done some iterative.
Yeah, they will do some testing. They will have past data, and then sometimes they will extrapolate. Sometimes they'll be overly aggressive with setting these limits, right? So they have past data and they have some familiarity with the system. So there's a chicken and egg type thing here, right? So you basically, same thing with binning. We collect data so we can predict what the good operating conditions should be, right? And you try to make it not too strict, but at the same time not too lax, that you are responsible for warranty claims. And again, this is a huge part of decision making. Like, how should we define the operating conditions? So when we, during my experience working with these systems, we had to always check for whether they can handle chemicals, what is the temperature limit that something can work at. And in one particular case, I remember that the water got hot enough that we had to have a heat exchanger to cool it down before it could recirculate it through the system, right? So the parts won't break. So that was a decision that we made, it's a cost-benefit type analysis. One way to do this is to buy high-end component. Every single component in the loop, then you start thinking of different materials, you start thinking of different, more expensive pressure gauges, more expensive sensors and all that, versus just cool down the water before you recirculate it. So you can do those kinds of things. And then we also need to define acceptable functionality. So just because it's there, it hasn't broken, doesn't mean that it hasn't failed. If it's not able to generate requisite pressure, it has failed, right? So if the Venturi should be able to generate a suction pressure of so many inches of water column, outside of this is a failure, okay? It may also be a failure if it generates too much negative pressure, of course, because then you may actually affect the experiments that are going on, right? So there you go. So, which gives us the opportunity to define formally what reliability means. Reliability of a component or a system at time t is defined as the probability that it will still be performing its intended function under the stated operating conditions. Okay, so this covers all the things that we've been saying. It is a probability. It has to be defined at a particular time. There's no vague reliability. This is reliable doesn't mean anything. Everything is reliable initially until you operate it a certain amount of time. it will be performing its intended function, right? Things that it's designed for, you can expect to do other things. Under stated operating conditions, we have discussed this already. So this probabilistic interpretation is useful because component performance cannot be guaranteed with certainty, okay? Even the best designed parts will fail. Even the worst designed parts may succeed. Such a definition is also mathematically rigorous. And once you have something like this, you can start making decisions. You can define warranty terms. You can do decision analysis. If you remember, the whole reason we did utility functions, or one of the major reasons we do utility functions, so you can capture preferences under risk, right? Utility functions are nonlinear, so they are nonlinear. They capture the preferences under risk. When you find the expectation of the utility function, you are actually taking into account the risk attitude of the decision maker. So when you have a formal definition of reliability, which is also probabilistic, it sort of fits right into, provides an input to your decision-making model. Okay, so now we can talk about the reliability function. Excuse me. So a reliability function is a mathematical expression that takes into account a system's construction susceptibilities and provides the probability that it'll still be working at or survive beyond a pre-specified time under stated conditions, right? So even though it's not explicitly taken into account what the system's construction is, what susceptibilities is, in time-dependent reliability problems we do. Okay, so when you have, let's say, a turbine or a hydrokinetic turbine that is working in a river, you will actually look at the input stream velocity as a stochastic process, okay? In which case, you will actually solve the stress-strain relationships using the velocity as one of the inputs. And then from that, you can get to the stress generated and then whether it will fail, okay? So in those cases, we explicitly consider the system susceptibility and find the probability of failure because we have a model of uncertainty, which is the stochastic process that the velocity or any other input follows. In time-independent reliability problems, which is the problem that we're doing right now, or the kind of problems that we will be talking about right now, that is, we assume that it's built into the distribution, right? It's implicitly taken care of by the distribution or the parameters of the distribution at hand. So, it is a decreasing function, and since it's a probability, it has to lie between 1 and 0. Or more accurately, it's a non-decreasing function. You have the x-axis, you have time, non-increasing function, I should say. On the x-axis, you have time. On the y-axis, you have reliability, and it looks typically like this, okay? So these are embedded, like I said, embedded in the parameters in the reliability function, okay? The system's construction susceptibilities and so on and so forth. And these parameters can be found by fitting data about the time to failure of many systems of the same type or analytically for time-dependent reliability methods, right? So same thing that I said. You can collect data or you can actually predict probability of failure at a certain time using time-dependent reliability methods. So I've worked quite a bit in the past on time-dependent reliability. Anybody who's interested in learning more about that, we can talk offline or you can send me an email. Okay, so as expected, this function is non-increasing. And for most products, it decreases monotonically, okay? So let's understand how this function can be derived. So we first define a random variable t, which is the time to failure, okay? Notice capitalization, which means it's a random variable. And small tb is realization, which is a specific value such as 254 seconds, okay? It's standard procedure for when we deal with random variables. So the probability that a given component will last longer than time t is the number of surviving components at time t divided by the total number of components, right? That we started with, okay? So reliability at time t is number surviving over number total at time t, okay? Which is the same as number surviving at time t over number surviving at time t plus number of failed at time t. Okay. And now using probability notation, we can write this as follows for a general case. The reliability is the probability that the component is working at time t, means that it only fails after time t. So R of t is probability that the failure time t, capital random variable, is greater than the time t. Okay. So another way to write this is RT is 1 minus P, that t is less than or equal to t. So where do you think you've seen this? That's the CDF, right? So just realize that that the second term is the CDF of the random variable t. So there you go. So that's the relationship between the time to failure random variable, which is the time to failure random variable, which measures the time to failure of a system. The CDF and the reliability function are related like this. Okay, so pretty basic concept, but it's important that reliability of a component or a system is equal to 1 minus the CDF of the time to failure. Okay. All right. So, and we always know that, if you have the PDF, we can get the CDF of a random variable and vice versa. So, since CDF at time t is when we integrate the PDF from negative infinity to that time, and then we substitute and we get this expression. Okay. Now, there's one thing that changed here is that instead of negative infinity, we replaced it with 0, because obviously there is no negative time. So ideally, practically the system didn't even exist before time 0, so no point taking into account those things. Let's see how I'm doing on time. Okay, so that's another way of writing the reliability function, which is 1 minus the integral from 0 to t of the PDF of the time to failure. Yes.
Just explain how did the second equation come? First equation I understood minus infinity to t. Like the second equation, how it is RT equal to 1 minus integral 0 to t ft dx.
Okay, two things happen, right? So reliability is 1 minus the CDF, right? So that's the CDF. So we write 1 minus the CDF. And then we already said that since there is no negative time, we can just do it from 0, right? All the integral from the negative infinity to 0 would be 0. So no need to worry about those kinds of things. No system will fail in negative time. It will only fail after time 0. Okay. So these are basically the same thing visually, right? So you have the reliability function decreasing and you have the CDF increasing. They both reach 1. So this measures the probability that you're succeeding at time t. FT measures the probability that you failed at time t. Okay. So we'll just do a pretty simple problem just to fully understand and get comfortable with these ideas. So you have a system's time to failure is given here. The CDF is given there. What is the reliability? Okay. Basic stuff, right? So just 1 minus that. Okay, so 1 minus that. So reliability at 0 times 0 is 1. Reliability at time 25 seconds is 1 minus 0.2 is 0.8, and so on and so forth. Okay, so nothing difficult here. Now we go to a slightly more interesting concept, which is failure rate of a component. Okay. So oftentimes, when you could just buy one chemical scrubber, you could buy 1 million chemical scrubbers. But we often are dealing with populations of components or systems, right? You could have a fleet of automobiles. You could have solar cells in a solar panel array, right? So you have a large number of those components. And we're often interested in how quickly the remaining components are failing. Okay, of the ones that I have so far, how many do you expect to last next day, and so on and so forth, right? So with that, we can make decisions on whether we should be doing preventative or condition-based maintenance, whether we need to replace the system or systems or components. So therein develops the concept of failure rate. Okay. The reliability function we have defined already gives us a lot of tools. Okay, so we can extrapolate from that many things about the statistics of a system failure, their operation, and so on and so forth. So the probability that a system fails at time t, which is between two arbitrary times t1 and t2, is given by this, right? So this time t is between two arbitrary times t1 and t2 is probability of failure at time 2 minus probability of failure at time 1. The converse of it is reliability at time 1 minus the reliability of time 2. This is the probability you're still working at time 1. This is the probability you're still working at time 2. The difference is the probability that you failed between these two times. Okay. So within this interval, we define failure rate as, and that's pretty simple, right? So is this expression where you have systems that are failing divided by the reliability at time 1 times the length of the interval in the denominator. Okay, so this tells you what fraction of the remaining, so this is the remaining, what fraction of the remaining components are failing per unit time. Okay, every hour, you could say 10% of the remaining components are failing. Okay, provided that they were working at the beginning of the interval. Okay, so you have to keep that into account, that if you have already failed, then you don't get into the equation. Okay, so yeah, and this is how we build concepts, right? I mean, it's still pretty straightforward stuff, but then it builds into things that get a little bit more interesting. Okay, so and then the related thing is the hazard function, right? So hazard function and failure rate are related. That hazard function or hazard rate is the failure rate for an infinitesimally small interval, right? And that's important here. So if we come back here and we look at failure rate and we talk about, like, fraction of units failing per unit time, well, yes, things are changing every second or every per unit time. If this interval is too large, then it starts becoming somewhat meaningless, right? So we can't say failure rate when we are talking about an interval between 0 and 10,000 years. That doesn't make any sense. Okay, what fraction of components are failing per unit time? Well, okay. So we talk about infinitesimally small intervals, and then now suddenly we need to take limits, and then we say t2 minus t1 approaches 0, and we get the following expression of the hazard rate. So hazard rate is negative of the derivative of the reliability function divided by the reliability function. In other words, it is the PDF at time t divided by the reliability function. And it really shouldn't concern us too much if you can just get it directly from this expression, right? So if you look at the denominator RT is here, and this part is just a definition of the derivative if t2 minus t1 is very small. Okay, so but this is a little bit more cleaner to work with. Okay, and then if you have the probability density function of the time to failure, you can get it directly, and if you believe it, you don't have to collect any more data. Okay, so sometimes the terms hazard rate and failure rate are used interchangeably. People will use them together. They equal each other for very small intervals, right? So like we said, one is the other. If the intervals are very small, you get the same, pretty much the same thing. Okay, so this leads us to our next idea, which is the bathtub curve. Have you all heard of the bathtub curve? Yes? Yeah.
infant mortality rate.
Yeah, so so a typical bathtub curve looks like this. It looks like the cross section of a bathtub. That's hence the name. So you divide a system's life cycle into 3 phases: infant mortality, useful life, and wear out life. Right. So you have T on the x-axis. You have hazard rate here, and you have 3 phases. You have decreasing failure rate. You have almost constant failure rate, and then you wear out life. So infant mortality is because in the initial stages, and that's something we see, right, that design flaws can happen. We may have made an error in designing a component. We may have made an error in assembling a component, or general manufacturing defects. A whole bunch of things can happen, right? So cause a lot of failure. So hazard function is decreasing in this phase, right? So this is the phase. Interestingly, so the conditional reliability, or the reliability at time t plus dt, condition on the fact that the system is working at time t, is increasing. So things are getting better for surviving components. That's what it means initially, right? Whoever survives infant mortality means that there was really no design flaws or anything there. Okay. Oftentimes you would catch those design flaws and manufacturing errors before you ship out the components or systems. So, and that's why many engineers propose test runs before a system is fully certified or used. And sometimes people even will say it's better to buy slightly used products than brand new, because the first owner would have taken care of all the issues. Okay. And the next phase, where most systems will spend most of their lifetime, is the useful life. In this phase, failures occur mostly because of chance events compounded by normal wear and tear. So you're driving on the freeway and then you hit a nail on the road. Okay, there's nothing a manufacturer can do about this. So really, there's really no manufacturing or design flaws that we can attribute this to. This is just chance events mostly. Okay, so this is where manufacturers will focus on reducing wear and tear and prescribe strict operating conditions. So you might say, you know what, failures might happen here. And some systems, let's say, that don't have design flaws or manufacturing errors, may survive infant mortality just because they're new, right? But they're actually difficult operating conditions. Those same operating conditions may not be survivable for an older system. So that's where manufacturers will be able to specify that, you know, in these conditions, the thing is expected to work. Hazard function is more or less constant as shown. And the third and last phase is wear out phase, where hazard function is increasing again. System is reaching end of life, right? So almost everything has degraded. Repairs are no longer worth it. Systems that remain need constant repair, and so on and so forth, right? So, and it's good for decision making too. So if you're here, then again, you have to think about whether you want to replace the system, or retire the system, replace the system, or continue repairing it. Okay, so here I have a few examples, right? So for infant mortality, you could say bulb burning out as soon as it is installed. Okay, manufacturing defect or something like that. A lemon car. I don't know if you're familiar with that term. Like a car that has some manufacturing defects that, you know, you buy it and it just keeps going back to the shop right away. So they call it a lemon. At least that's the US terminology. And then a truss structure fails because of faulty construction. We had a failure recently in, I think, South Korea, right? That a span just collapsed. Useful life, hail damage to the windscreen of the car. I don't control the weather. Manufacturers don't control the weather. Power plant damaged by an earthquake. Cell phone damaged after dropping it in water, right? Chance events. There's really nothing you can do about that. And there's no design flaws you can attribute to, no reliability issues you can attribute to. Wear out life is, I mean, just 3 examples. 50-year-old power plant in constant need of repair. Okay. They just closed down a whole bunch of old power plants, nuclear power plants in Europe, and then also coal-fired power plants all over the world, because it's just not worth replacing them. An obsolete cell phone. and a battery that does not maintain the requisite voltage. Okay, so this leads us to the Weibull distribution. So Weibull distribution is a commonly encountered distribution in reliability engineering, which closely models the time to failure for most systems that we encounter. Often other distributions such as the normal distribution can be used if it better models failure data. So, right, we're not married to Weibull distribution. We use whatever distribution works better. But since we see Weibull distribution so many times, and there's some theoretical reasons as to why that is, I don't want to get into that, but we see it often, so it's good to know this distribution, right? So here's the PDF and CDF of the Weibull distribution. So on the top you have the PDF of the Weibull distribution, and the bottom you have the CDF. Lambda is called the scale parameter and has the units of time, and B is the shape parameter, right? So you normalize time with this lambda. Of course, it has to have the units of time, and then B is the scale parameter. So if we just focus on this, we see that number one, it's a relatively easy function to work with, but since reliability is 1 minus the CDF, you just get this expression, okay? And this expression will be 0, also will be 1 when t equals 0. So it all falls into place, okay? So there you go. So the reliability function of a system whose time to failure follows a Weibull distribution is given by this. Pretty interesting distribution to know. And the hazard rate is given here, okay? So you can just get that from using the expression I showed earlier. So there's, again, nothing too difficult here, but just some things to know if you want to work in reliability engineering. So a basic example, you have a scale shape parameters of 30,002. What is the reliability and hazard rate at 1,000 hours? So we just plug the numbers into the equation, we find the reliability, and the hazard rate is this much. So of the remaining components, so many 10 to the negative 2 times 10 to the negative 5 fraction are failing at 10,000 hours. Okay, so when you have a large circuit, you have a lot of transistors, or you're dealing with a lot of transistors, then you may want to consider this number. Okay. What is the probability that it fails between 15,000 and 20,000 hours? Yeah, so it's reliability at time t1 minus reliability at time 2, right? So pretty straightforward again. Just practicing straightforward concepts for people that don't know. Okay. Okay, so welcome back. We'll be talking about, we'll continue examples here. So failure data, right? So we know what reliability is now. We had decided, let's say, that the venturi should be able to generate suction pressure between 4 and 10 inches to be considered functional. So if you go outside of that bound, you will be considered failed. Just something to point out that sometimes we add sensors to these systems, right? So we can actually, I think that the system we built had a sensor, so we'd like to keep track of the pressure generated, or something similar that it will log when something has failed, right? So even if somebody doesn't report it, there's a log of what the pressure is generated, so we can actually create distributions, and we can actually, even before it has failed, we can find out probabilities of something failing, right? So if, let's say we have lots of data, we find the mean, and we see that it's normally distributed, we find the mean and a standard deviation, we can say the probability that it will exceed this is that, right? So, so failure can be derived using in-house testing. We discussed this earlier, and even accelerated testing, right? So that's something that we do quite a bit of in engineering. So we can't wait for years for a system to fail. So sometimes we subject them to harsher operating conditions to see failures, and then we scale it back to what happens if the system was subjected to normal operating conditions. Okay, yes. So accelerated testing is used when we want to reduce the time to failure of components, right? So this is a pretty common technique. There's a lot of papers on this if you want to go read them. Right, so let's say that we had data for the operation of 32 Venturis, and they look like this, right? So I showed you a small graphic of 5 or 6 Venturis failing at certain times. Let's say we were able to collect data on 32 Venturis. Okay. So what do we do now? Or what should we do now? We can fit a reliability function. That's one thing that we can do. Okay. So the beauty of actually having formal models of uncertainty in engineering, right? So as opposed to just saying, here's raw data and live with it, versus trying to see what it's telling us, right? So if we actually fit a distribution to that data, then we have formalized our understanding. Formalized as in we're using a sort of a benchmark of what's going on. We can reasonably, you should not extrapolate or interpolate too much, but we can reasonably extrapolate and interpolate, right? So that if we had, right now we have 32 data, if we have 32,000 data, what do you think will happen in that case? How many will fail? Another example that you can do is this that we see here, right? For example, for the data shown in the previous slide, which is this data, let's say I'm interested in the failure between 70 and 100 days. You would think that the probability is 0, right? Because nothing fails. If you look here, nothing fails between 70 and 100 days, right? So that's why raw data is important, but tell us what story it's trying to tell, figure out what story it's trying to tell you. And that's obviously incorrect. It's not that, nothing fails between 70 and 100. It's just the artifact of this particular data set that we collected. The other thing in that is critical, right? So if you are really interested in warrantying a system and you said, okay, we'll warranty for, 90 days. Okay, you want to know how many failed before 90 days. And luckily or unluckily, you don't have raw data, but you can get that data. Okay, and then we can make warranty decision, what warranty terms to offer, what percentage of components are expected to fail in the warranty period. So you can see, okay, well, we offer failure-free 90 days. That means, but our calculations show that 3% of the systems would have failed. So then you can plan accordingly, right? That I expect this much failure to occur in that period. Huh?
Warranty is also trade-off. If we give high warranty, the demand will be at what cost? Warranty will be at.
Yeah, so warranty helps with brand image. Warranty helps with getting your customers. So yeah, it does actually improve your sales a little bit, right? If you offer aggressive warranty terms. But it should not be completely oblivious to the product that you're selling, right? If your product is unreliable, don't have aggressive warranty terms because you'll be going broke pretty quick. And similarly, you should not be too lenient, too aggressive the other way either. Don't offer very small warranty terms because then you start affecting your sales, right? Okay. So we already agreed that the viable distribution is a good model for the distribution of time to failure. So there are many ways you can fit distributions to data, right? So you can use the maximum likelihood method, you can use moment matching, you can use percentile matching. There's a whole bunch of techniques available, okay? And you're free to use any of those. So, and a software like Minitab will do it for you very easily. You can say that, here's the data, fit a distribution, will do that for you. So we'll use percentile matching just to show how it could be done. sometimes we have to smooth data, but then let's not worry about those kinds of things here. So we all know what percentile is, right? It is the value of the random variable below which a certain percentage of realizations will lie. So therefore, a 50th percentile is a value below which 50% of the observations will lie. For example, after sorting, we see that 50% of the realizations lie at or below 182 days. Okay, so we tabulate these percentile values. Of course, these are there could be errors with any of these methods. So we continue like this: the 0th, 25th, 50th, 70th, 100th percentile. Find the corresponding value, and that gives us the CDF value, right? So CDF, we assume that we can also assume that it is equal to 0 at 0 days, right? So you can add those kinds of things to your model to make sure it reflects reality and so on and so forth. Okay, so fitting viable distribution, we did this, I think, using Excel solver. So fitting a viable distribution means finding the parameters. The parameters of viable distribution are shape and scale parameters, the lambda and b that I talked about earlier, right? Because at t equals 0, the CDF is 0 and the reliability function is 1. That's a known fact. The only thing you need to know is the scale and shape parameters of the viable distribution. Okay, so here's that, and the solution is given below. So now we compare to see if we got any decent fit, and then it looks like we did, right? So you're sort of using your knowledge of optimization. When you're doing curve fitting, you're actually doing optimization. You're minimizing the error. So we find scale parameter to be 202, shape parameter to be 2.4, and it goes like this. So we can see that it sort of fits the data reasonably well. Here we have the CDF, fitted CDF and the given data. Okay, so now we can make other decisions, right? We're not just limited to finding percentiles of portions of or the fractions of systems that fail or succeed at a certain time. We can extrapolate and interpolate a little bit. Okay. So what is the expected number of warranty claims for the Venturi if the manufacturer offers a 30-day warranty period? Another question is, what is the reliability of Venturi at 100 days? Expected number of warranty claims is basically expected number of failed components, right? It is 1 minus the reliability at the end of 30 days, whatever succeeding, which is same as the CDF at 30 days, okay? So, pretty easy stuff here. We already have the function. We already found the shape and scale parameters. So we plug those in, and then we find that about 1% of customers are expected to come back in 30 days with some failure, okay, based on the data that we have and the model that we have. And hopefully the model we have is correct. And then the reliability of the Venturi at 100 days is, again, we use the reliability function, which is, this is 1 minus the CDF of the viable distribution that we found, and it comes out to 0.832. Okay. So the caveat I have for any such data that I present is that, obviously do your own calculations. I mean, there may be errors in the slides. I hope not, but there could be. Okay. So the more important thing is the method, right? So now, just to summarize, we can have data, we can fit distributions. Data allows us to do distribution. Just want to look at something here. There's only one component that failed below 30, right? So I guess this gives us about what, 3% probability of failure if we just relied on this. But when you fit a distribution, it looks at the entire shape of the distribution and it finds a much better number. So the number we found was, hang on, sorry, for 1%. So we expect about 1% to fail before 30 days. And then reliability in 100 days is 83%, which means 83% are expected to be working at 100 days, which about 16.8 should be failed by 100 days. Okay.